Hey guys, my goal in this video is to convince you all that implicit differentiation is not this big, scary, intimidating, formidable thing that a lot of people think it is. I honestly don't really know why it gets such a bad reputation. I think it could be like that it's not commonly understood why you do what you do in the implicit differentiation process. So if you want to get a good like foundational understanding of like the why, then I would refer you to 3 Blue 1 Brown because he's got all those fancy animations and he's a really good explainer and all that stuff. But if you just want to be an executioner, if you just want to like follow the recipe and the process, it's super like not a big deal. In fact, I'll just tell you, if you have a equation that has like a y term in it, so if you have like y to the fifth, you have to do implicit differentiation, and all that entails is you do the derivative like normal. So like here you would do the product rule, or the power rule, sorry, and then you just add a dy dx. And that's the end of the list of things that you need to know, seriously. And then maybe you'd have to do one more step at the end, which is like isolate dy dx. But that's it. So it's not that bad. I'll do a couple examples. So I have an easy example here. I have a medium difficulty example, and then I have a hard one. But the varying levels of difficulty is just because it's more or less algebra steps that you have to do. But at the core, implicit differentiation is like the same thing as normal differentiating, like explicit differentiating, just like an extra step or two. So let's jump in with this easy example. You have an equation x equals y squared, which is this sideways parabola. And so if you want to find an equation for the slope of the tangent line at any point, dy dx, then you have to do implicit differentiation. And the reason for that is because this isn't a function. You don't have a function like f of x equals an expression of just the variable x, right? Like this doesn't pass the vertical line test. So those are the times where you have to use implicit differentiation. And like in the next problem, it's a circle, that's not a function. And in the hard problem, it's a heart, that's not a function either. So that's when you know that you're going to have to do it implicitly. And so let's just do the process. So the first step is always to do d dx of both sides. So we'll do d dx of the left side, which is just x, and we'll do d dx of the right side, which is y squared. So on the left, that's pretty straightforward. It's just equal to 1. And then on the right, we do what we just talked about. So you do the derivative like normal, which would use the power rule, you get 2y. And then you have to multiply by dy dx. And if we want to find dy dx, this is that second extra step that you have to do in implicit differentiation. You have to do a little bit of algebra to isolate dy dx. But that's not bad in this example. You just move it to the other side, the 2y to the other side, and you get that dy dx is equal to 1 over 2y. And that's your answer. And you move on. And one thing I like to do when I get the final answer is do a quick sanity check. So let's plug in a couple y values on this curve and see if the slope of the tangent line at that spot of the curve makes sense when you plug in y for 1 over 2y. So like if you plug in 0, you'll get 1 over 2 times 0. That's like infinity. So it's a vertical tangent line. That makes sense. And if you plug in a positive y value, you'll get a positive slope, right? So if I plug in like y equals 1, I'll get this positive slope here, which makes sense because it's 1 over 2 times a positive number. And if I plug in a negative value for y, I'll get like a negative slope because it's 1 over 2 times negative, which would be a negative slope. All right, let's move on to the next problem. We have this equation for a circle with radius 10. And we want to find, just like in the previous example, an expression for the slope of the tangent line at any point x comma y. So like if we wanted to plug in this point here, I don't know what that would be, but like x comma y, we want to plug that into some formula and it would spit out the slope of this tangent line right here. And because this circle isn't defined in terms of just x, it's defined in terms of x and y together, we have to do implicit differentiation. But now you guys know that that's not a big stressful thing. You just do a couple extra steps. So the first step is always d dx of both sides. Okay, so on the left, we can distribute the derivative because the derivative of a sum is the sum of the derivatives, right? That's a property of derivatives. So we get 2x, that's pretty straightforward derivative, and then 2y, but because we're doing the derivative of this y expression, we have to multiply by dy dx. And then on the right, we just get 0, right? The derivative of any constant is 0. So now we just isolate dy dx. And how do we do that? Well, we move the 2x over to the right side. So we get 2y dy dx equals negative 2x, and we divide by the 2y. So this is negative 2x over 2y, and then we can cancel out the 2's, and we get negative x over y. And then we can do our sanity check again, right? Like if I plugged in a positive x value and a negative y value for this point, I would get a negative x over a negative y. That's a positive slope, just like you'd say. And you could do a sanity check for points in all 4 quadrants, make sure the slope of the tangent line makes sense. But here we go, that's our answer for dy dx. All right, you ready for the beast? So this, I don't know how anyone came up with this, but apparently this is the equation that defines this curve that looks like a heart, okay? And what we have to do is find the slope of the tangent line to this heart curve at the point -1, 1. So these are some points on the graph, and we want to find right here what is the slope of that tangent line. So if we get a negative slope, we know we did something wrong, okay? Again, this is only hard because it's more difficult algebra, but the process is the same. So first step, we do d dx of both sides. All right, this right side is the derivative of a constant, so it just goes to 0. And the left side, we got to do some distributing. So we'll do d dx of this first term, this cubed term, minus d dx of this x squared y cubed. Okay, what do we do next? So if we want to do this first derivative, we're going to use the chain rule, which you do by treating everything in these parentheses as just some block that you don't really care about, and you do the power rule like normal, and then you multiply by the derivative of the inside. So we would get that this first derivative is 3 times the quantity x squared plus y squared minus 1, and then we decrement the power by 1, and then we multiply by the derivative of the inside. So I'll say times d dx of this x squared plus y squared minus 1. And then we're going to do this derivative here. Here we're trying to do d dx of the product of 2 unknown variables. So we have to do the power rule, right? Which is the same process in implicit differentiation as explicit differentiation. But now we just have to do that extra dy dx when we're doing the derivative of a y term. So we'll do it like normal. So we'll do derivative of the left term times the original right term plus the original left term times the derivative of the right term. Keeping in mind that when we do the derivative of y cubed, it'll be 3y squared, and then we have to multiply by that dy dx. Okay, so do you guys agree with what I have here? I did y cubed turns to 3y squared dy dx. Also make sure that you keep this negative sign out in front because it's negative. You're subtracting this entire derivative, so you would have to distribute this negative sign when we ultimately do that. But anyway, now we got to do one more derivative, and then I'm going to give you a tip so that the algebra doesn't get absolutely out of control. So now we have this 3 times the quantity x squared plus y squared minus 1 squared times this derivative. So this is easy. You distribute this derivative across the sum. So we get the derivative of x squared plus the derivative of y squared minus the derivative of 1. So this is just 2x plus 2y, and then we have that dy dx. And then the derivative of -1 with respect to x is just 0. Okay, and then we still have this minus 2xy cubed plus x squared. We can rearrange this term a little bit, make this plus 3x squared y squared dy dx. Oh, and I've dropped this equals 0, so don't forget that we have this equals 0 on the right. Okay, so we have this whole mess, and like in the easy and medium problems, we were isolating dy dx as a function of x and y. And if you try to do that with this, you're going to lose your mind, right? You're going to have to do all this foiling and distributing and rearranging, and no one wants to do that. So go back to the original question. What is it asking for? We just want to find dy dx at the point -1, 1. So hopefully you have this realization going through the problem. And if you didn't, keep it in mind for when you take your tests. You can just plug in at this point, before you do any more algebra, after you've gotten rid of all your derivatives, you can plug in x equals -1 and y equals +1, because that's the point at which we want to find dy dx, and that'll simplify things a bunch, because it'll get rid of all these terms. You can combine stuff. Like this x squared plus y squared minus 1 will just become what? -1 squared plus 1 squared minus 1. That's 1 plus 1 minus 1. That's just equals 1, right? And then we have 3 times 1 squared, which just equals 3. And so just like that, all of this collapsed into 3. So I'm going to go ahead and plug in these values for x and y, and we'll see how much it simplifies. Okay, so we're super close. So in this first row here, I plugged in -1 wherever there's an x and +1 wherever there's a y. This simplified to the second row, which simplified further to this third row. And so now all that's left, we'll distribute this 3 to these two terms. So we get -6 plus 6 dy dx. And then we have +2 and we have -3 dy dx. My handwriting's getting kind of crazy because we're so excited. And then, let's see, we can combine this term and this term. So we just get 3 dy dx. And then we have this -6 plus 2 is -4. This all equals 0. So what does this tell us? This tells us that the final value for dy dx evaluated at x equals -1, y equals 1 is equal to 4/3, right? Let me write this better. That's an ugly looking 4/3. Equals 4/3. Boom. And so that's good that it's positive, right? Remember I said if we didn't get a positive slope, we know we did something wrong. So 4/3 makes sense. And then maybe the question's worded a little different. Maybe it says, instead of find the slope of the tangent line, what if it just said find an equation for the tangent line? Well, then you have to reach back into your Algebra 2 toolkit. Maybe Algebra 1? I'm not sure. But use like point slope form or something. So if you wanted to find the actual equation for this tangent line, you could do what? y minus y1 equals m times x minus x1. And then we know m, that's dy dx evaluated at -1, +1. Right, and then we know y1 and x1 because we were given this point. So like the equation for this line is y minus 1 equals 4/3 x minus -1, so x plus 1. Right, that's the equation for this line right there. Okay, so these examples amounted to a heroic effort of algebra work, but I hope you now agree with me that implicit differentiation is explicit differentiation with a bad reputation. But it's actually pretty straightforward, and so I hope this video helped you, and I hope you do well on your test.